Hello, Algebra 2 students. This is a lecture on finding sums of infinite geometric series. Before we begin, let's break down each of these terms so we can understand what we are studying. If you recall from the previous lectures, sums in series are some two new words that we've talked about this chapter, and both of them really relate to the same thing. What we're going to be doing is we're going to have some pattern, and we're going to be adding up the consecutive terms, right? That's what you do with a series. It's a sequence if it's just a list of numbers, and it's a series if you are adding them up and finding their sum. Geometric is not a shape that we're talking about. Remember, geometric means that the terms, consecutive terms are being multiplied by the same thing every time. So an example of a geometric series would be something like 2 plus 4 plus 8 plus 16, where every term is being multiplied by 2, and because it's being multiplied by the same thing, we know it's geometric. And then infinite means that this series goes on forever. Now, this, I think, should appear like a contradiction to you. So if we are to take what this is asking for, right, we're adding up terms forever, and they're being multiplied together, or consecutive terms are being multiplied, and we're adding them up forever, that there should never be a sum, or that sum should always be infinite. If you add up a bunch of numbers forever, and they're being multiplied, like this series, if you did this forever, 2, then you added 4 to it, and then you added 8 to it, then you added 16, then you added 32, and you continued to do that forever, it seems like that answer should always be infinite. But there are some unique situations. This is not one of them, right? This is not, this is a geometric series, and it is an infinite geometric series because it's got that dot, dot, dot. But this one here would have no sum. But there are some unique situations where when you add up the terms forever, you do get a finite number. And so I know that it kind of seems weird. This is a very abstract lesson in general, but there are some infinite SOME. There are some infinite geometric series that do have sums, and those are going to be the ones that we're mostly studying in section 12.4. I want to start off by just giving an illustration for what this might look like. Let's imagine that my classroom is here. Here's the doorway. Here's the little hallway you walk in, and then here's my classroom. And here is the whiteboard on this wall, and my desk is over here. Okay. Let's say that we measure this room, and it's 32 feet across. And generally when I would teach this lesson in live, I would actually have a student stand up, and we would go through this illustration together. So let's say that they're on this wall, and I say, walk halfway to this wall here. What they would end up walking would be how many feet? Well, they would walk 16 feet, right? If I told them to walk halfway. So now student is here. They're very happy because they're in front of the class walking. They're having so much fun. Look at that smile. That's a smile. Ear to ear. Okay, so then I say walk halfway again. How far are they going to walk? Well, now they are going to have walked 8 feet total. 16 the first time, and then 8 the next time. And then I keep doing this. The next time I say, okay, walk halfway. Well, then they walked 4 more feet. And then they walk halfway, and then halfway, and then halfway, and then halfway. If they did that forever, now we're going to be dealing with very small fractions here. But if we did that forever and they always walked halfway, they are maybe gonna, if they did it forever, literally forever, they would eventually walk how far? Well, they would eventually walk 32 feet. I think you'd agree with me that they would never walk over 32 feet, right? It doesn't make sense because the room is only 32 feet across. But if they're always walking halfway, they're never actually getting that full distance to 32 feet. Now, if we say that we did it forever, we can say, hey, they walked 32 feet, or we can say they're approaching 32 feet. But they're never going to walk over 32 feet. And these are the types of situations that we're going to be studying today. So our numbers would have been 16 plus 8 plus 4 plus 2 plus 1 plus then a half, and then a fourth, and we could have kept going forever. Those numbers, if we follow that pattern forever, are never going to reach above 32 feet. And this is a geometric series. Our A1, our first term, is 16. Our R value, what we're multiplying by between consecutive terms. What do we multiply 16 by to get to 8, or 8 by to get to 4, right? Hopefully you're seeing that the R value there is 1/2. Or the other way to find the R value is to take a term and divide it by its previous term. 8 divided by 16, 4 divided by 8, 2 divided by 4, 1 divided by half. That'll tell you the R value, and you're going to find out that it's 1/2. So this is an illustration for what we're talking about today. I'm actually going to skip that illustration because I like the classroom one better. The sum of an infinite geometric series with first term A1 and common ratio R is given by this formula. So we're going to have this nice formula. It's not very complicated, but it's going to tell us what the sum is of an infinite geometric series. I want to point out that we're going to switch to S. I know in the previous couple sections we've been like, hey, what are the sum of the first 8 terms? Or what's the sum of the first 20 terms? If you were talking about an infinite sum, you don't put S sub infinity, because basically we just say, okay, S. Capital S means sum of the infinite terms. A1 is the first term, R is the common ratio, and this is a really critical part right here. This formula only works when the R value is between -1 and 1. If the R value is greater than 1 or less than -1, the series has no sum. If the R value is between -1 and 1, then it's like this example here. The R value in this is 2, because you're multiplying by 2 every time. Therefore, this series will have no sum, or if you added up the terms forever, it would be like infinite. This sum here, this formula here, though, does have a sum. If we did the same thing, we use our formula, okay? A1 we decided was 16 and R was 1/2. Let's use our formula. A1 is 16, so the sum of the first, sum of all of the terms is 16 divided by 1 minus 1/2. Well, 16 divided by 1/2 is 32. What do you know? Our formula matched up with what we decided with the situation, right? What are we going to walk? We're going to walk 32 feet in that example if we did it forever. And that's exactly what we ended up with this formula. So let's look at some examples here. One type of example is going to give you information in summation notation like this and expect you to find the sum. This is the easier type. This is very simple. Because think back to the lesson on geometric series and sequences in general. When you write a rule, the way to write a rule of a geometric series is a sub 1 times r to the n minus 1. And when you write it in summation notation, it's going to be using that rule. So we know what a sub 1 is. We know a1 is 5. We also know what r is. We know r is 0.8. So then we just get to plug these numbers in. A1 is 5. 5 divided by 1 minus 0.8, or 5 divided by 0.2, and 5 divided by 0.2 is 25. So if you added up these terms forever, you plugged in 1, then you plugged in 2, then you plugged in 3, 4, 5, 6, 7, all forever. What you would find is, and then added up all of those terms, what you would find is they add up to 25, or they are approaching 25. What about this example? The A1 is still 5 here, and the R value is 1.3. Now I'm going to get a ton of students who go through this work, they plug these numbers in, and then they get some number, and that some number will just be like any other number. They think that it's right. However, remember, this formula does not work if the R value is outside of the -1 to 1 range. Remember, the R value must be between -1 and 1. This example here, the R value is 1.3, and so the terms are going to be getting bigger between each consecutive term. So this has no sum. That's exactly what you're going to need to write in order to get the points. It does not have a sum, or if you did think of adding up all of the terms, it would be infinite. The other type of question that I'm going to be asking you is I'm going to give you the geometric series. This ... is to say that this goes on forever, and I'm going to expect you guys to find the sum. A1 is really obvious. A1 is given to you. A1 is 2, but the R value is a little bit more tricky if you're not very, if you don't have a good grasp of what we're doing. Remember, R value is what you're multiplying between consecutive terms, what you're multiplying by between consecutive terms. Or you could think of it as take a number like -3/2, this here, and divide it by the previous number, 2. Or take 9/8 and divide it by -3/2. Or take -27/32 and divide that by 9/8. And you should get the same number every time. When you do this, the number that you're getting is 0.7 or -0.75. -27/32 divided by 9/8, -0.75. 9/8 divided by -3/2, -0.75. That should happen every time. And so that is how you can acquire the R value so that you can plug it into the formula. 2/1 minus -0.75, or 2 divided by 1.75, right? Because 1 minus a negative is plus. So 2 divided by 1.75 is, and I would actually prefer the fraction answer, but if you give me the decimal, make sure you round it pretty good. You get 1.1429, we'll say. I'm going to give the approximately symbol. However, the fraction would have given you the great unrounded answer. That's what I would prefer. Remember, to get the fraction on your calculators, on your graphing calculators, push math and then frac. That's what I have for you guys for section 12.4. Please let me know if you guys have any questions. Thanks.